Hi everyone, I'm Dan, and in this video I'll be showing you how to perform image search using KDB.ai. Now, if you want to follow along then great, we just need to complete a couple of steps to get you started. The first is to sign up for an instance of KDB.ai Cloud. It's super simple, it doesn't require a credit card, you only need to add your contact details and hit the sign up button. Once done, you're going to want to sign into your instance and grab your endpoint URL and API key. Now we're going to need these later in the demo. Finally, let's head over to the Learning Hub where you'll find a whole bunch of resources to quickly get you up to speed with vector databases and generative AI. Now again, today we are covering image search. So what we'll need to do is pull down the notebook from GitHub and install any prerequisites that may be listed in the repo README. Great, so let's switch over to the notebook and import the packages that we're going to need for the demo. To do so, we're going to select the first code cell, then hold Shift and Enter to execute through them sequentially. Perfect. So the dataset that we're going to be using today contains a series of brain scans that have been pulled down from Kaggle. The rationale being that when applied to a powerful vector database such as KDB.ai, medical professionals will be able to compare scans against other patient cases and help diagnose tumors. Now, to save time, we've taken the liberty of resizing the images so that they're optimized for model training. We've also defined the pixel intensity and renamed the images to correspond to the tumor type. So let's go ahead and extract our image file paths, then use the plot image function to visualize the results. As you can see, 4 categories are returned. These are meningioma, no tumor, glioma, and pituitary. Finally, let's save each image into a new class label based on the folder category in which it's stored. Now, as you can see, this returns 394 files. Great. So let's now look at creating our embeddings. But before we do, let me give you the 30-second elevator pitch to make sure that we're all grounded in their meaning, context, and function. So a vector is a mathematical way to represent a fixed array of numbers that represent both magnitude and direction. This can run into the thousands, which is obviously cumbersome for humans to conceptualize, but perfect for machine learning applications. Vector embeddings, therefore, simply refer to a vector that contains a numerical representation of typically non-numerical data objects. Think things like text, images, and video. Now, these embeddings are used to capture the inherent properties and relationship of the original data in a highly condensed format. For example, we know that images contain millions of pixels, each with a unique color, hue, and contrast. So our embeddings can therefore be used to encode the relevant information about this data into a lower dimensional space, and this ensures efficient storage, retrieval, and computation. To create the embeddings, we need to transform our data through an embedding model, in this instance, ResNet 50. Now, ResNet is a type of artificial neural network designed to recognize and classify images into object categories, and it does so by analyzing the features of an image and then using them to make predictions about what the image contains. To achieve this, it uses a technique called residual learning, a process of skipping over some of the layers in the network to learn the differences between their input and output. To simplify, let's explore the following 4 layers. The first is ResNet 50, which in fairness is actually many layers umbrellaed under one name. Then we have our flattened layer, which turns our outputs into a 2048 dimensional vector. Finally, we have the dense layers, which help create the 4-dimensional classification of the input image. Now, in fairness, we don't actually need the classification in today's demo, so we'll strip those back by using the pop command. Perfect. So let's now create our embeddings by iterating through our dataset and saving to a corresponding class vector. As you can see, we end up with 394 records, listing the source, class, and embedding. So now we want to visualize our embeddings. To do so, we're going to reduce them down into 2 dimensions and then plot them into a simple cluster chart. And this is where things get interesting. Notice that glioma, meningioma, and no tumor are fairly well clustered, but pituitary seems to be dispersed. In real life, this signifies that more training is required. But perhaps more interestingly, notice the meningioma plots that seem to have found their way into other categories. Could that represent a misdiagnosis when the original labeling occurred? The point I'm trying to make is that even with minimal training, the AI model and subsequent nearest neighbors have uncovered something that may have been missed by a medical professional. Anyway, some food for thought. Let's move on and get our embedding stored into KDB.ai. Now, to do so, you're going to need that endpoint and API key that you retrieved earlier. For me, I've already added these as variables, but if you're following along, go ahead and paste them into your notebook now. Perfect. So we're now all connected into KDB.ai. Let's define our schema, which in this instance will contain 3 columns. One for the embedding, one for the class, and another for the file paths. Also, pay attention to the method of similarity and index type. In this instance, we're going to be using Euclidean distance, which assesses the similarity of 2 vectors by measuring the straight line distance between the 2 vector points. Simply speaking, the shorter the distance, the more similar the vector. For our indexing, we'll be using HNSW. Now, this is a type of proximity graph that connects vectors into a network-like structure. To that, each vector connects to its peers via a friends list and traverses the network until it finds the nearest neighbor to the original query vector. Now again, please don't worry if this is new to you. We have plenty of documentation about these methods over on KDB.ai and a community of professionals happy to answer any questions you may have in our Slack channels. Bottom line, we want you to be successful. Anyway, let's create and save our table, then add our embeddings. Now, as a side note, when you're adding larger amounts of data to your index, you're typically going to want to break them up into smaller chunks. This will help streamline vector processing and subsequently reduce computer load. The recommendation is around 10 megabits, which, as you can see, we're well under in this instance. Great! So now we have our embeddings stored into KDB.ai. Let's test them out by filtering for images that contain the word glioma in the file path. As you can see, this returns a table from our embedded training dataset. But there's more. You see, we don't want KDB.ai to search via file names. Any database can do that. We want KDB.ai to return results based on a similarity score. So let's go ahead and perform another search, this time selecting image 40 from our test dataset. Now, what will happen in this instance is the vector data of image 40 will be saved into a new variable, and KDB.ai will then perform a similarity search, returning the 8 nearest neighbors into a nicely formatted table. We can also plot the images to compare diagnosis, which again lists them in this instance as glioma. Okay, let's try one other example, this time selecting image 210. Now, moving straight to the image plot, we can see that the diagnosis comes back as meningioma, proving once again how powerful the similarity searches can be in this type of activity. Now, unfortunately, this brings us to the end of today's demo. It's my hope that you found it informative and were able to follow along. Remember, we have a whole bunch of samples, articles, and demo videos over on the KDB.ai Learning Hub. You can also subscribe to our channel where we'll be posting lots of content over the coming weeks. Thank you.